Everyone, in this video lesson, we're going to do a bit of an introduction into projectile motion. So what is projectile motion? What are the key ideas behind it? And we'll start looking at some examples. Specifically, we'll do an example with horizontal projectile motion. So let's get started. Most of you guys are kind of young, but you probably are familiar with Wile E. Coyote and Roadrunner. And a classic bit with this cartoon was Wile E. Coyote would be chasing Roadrunner, and he would for one reason or another he'd always run off a cliff. And sometimes he'd run off and he kind of wouldn't start falling down until he looked down. But people actually believe that's kind of how projectiles behaved. They thought, that a projectile would follow a straight line, kind of like Wile E. Coyote off a cliff, until they ran out of something, their impetus, let's say, and at that point they drop out of the air and then they would just head straight down. So we know that the way Wile E. Coyote falls off a cliff, we know that's not the way that things happen in real life. At this point, I would really encourage you to play around with the PhET simulation that's on Brightspace, or if I move my handsome face here, you could use a phone to screen capture, maybe snapshot the QR code there. It would take you to the simulation, and I would encourage you to play around with it. I have it loaded up here, so I'm going to head up here as well. So this is just the intro of this simulation, just allowing us to play around with a few things. And something I want to show to you guys. So first of all, note that I have the initial speed set to 0. So whatever I'm firing out of this cannonball, it's actually just going to fall straight down. So here we have a pumpkin. And sorry, I'm going to sneeze. Excuse me. I feel like I'm going to sneeze again, but we'll deal with that when it comes. But yeah, I can fire this pumpkin, and you can see the pumpkin fall straight down. And one thing I'm going to do throughout here is just I'm going to investigate the time it took. So in this case, it took 1.43 seconds for our 5-kilogram pumpkin to drop this height of 10 meters. Something that you guys would have investigated and learned in your grade 11 course is that the pumpkin and, say, a cannonball, they're not going to accelerate at different rates. The acceleration due to gravity is just the acceleration due to gravity. And our equations of motion have nothing to do with mass. So we have the cannonball with a mass of 17.6 kilograms. If I clear everything, get back to cannonball. Get back to a 0 initial speed. I drop that cannonball. Oh, we're still in the pumpkin. Good grief. Cannonball. Drop the cannonball. Now it's firing it. Oh boy. Cannonball. Ultimately, it doesn't matter. We show the same thing, but cannonball, initial speed is 0. Drop in the cannonball. There we go. If you see the time it takes, it's the same time, 1.43 seconds. And so neglecting air resistance, which you see I have turned off, things accelerate at the same rate, due to gravity. It doesn't matter what their mass is. Of course, we know that things that have, maybe a large surface area or a lot of drag, like dropping a piece of paper, they might have a different acceleration. But near the Earth's surface, all objects fall with the same uniform acceleration, dropped in this acceleration due to gravity. If we neglect air resistance, if dropped from the same height, 2 different objects will hit the ground at the same time. So we all know that this is a simplification and that air resistance plays a part, and that acceleration due to gravity is around 9.8 meters per second squared, but that changes depending on the elevation you are above the Earth's surface. and various other factors as well. But for the most part, we can accept this as mostly true. I would encourage you to play around with the PhET simulation more, especially to verify what we're going to look at next. So we just dropped that cannonball. Its horizontal speed out of the cannon was 0 meters per second. But what if I launched it with a speed of 5 meters per second? Would it take longer, the same time, or a short amount of time to hit the ground? So remember, we're keeping off air resistance. Maybe think about that. Maybe try it yourself on the simulation. But here we go. So obviously, if we gave it some initial speed horizontally from the cannon, it's going to travel some distance. So we hit our guy. Good thing he's okay. But check this out. The time it took that projectile to reach the ground was still 1.43 seconds. And if I launched the cannonball with a faster horizontal speed, oh, congrats, I hit the bullseye, it also took the same amount of time. In fact, it doesn't matter what the horizontal speed is. If I project this horizontally, it all reaches at the same time. So this actually indicates a really interesting idea, that a projectile and the concepts, the equations that govern the motion of a projectile in 2 dimensions, there's some rules for the y direction, and there's some rules for the x direction, and they don't necessarily affect each other. So, for example, what we've seen here is that in the y direction, the cannonball hit the ground at the same time, no matter what the horizontal speed was. The vertical motion was just acceleration due to gravity. And if we look at the horizontal motion, check this out. So in the first one, see if you can make a connection. So with a speed of 5 meters per second, we had a range of about 7.14 meters. With an initial speed of 10 meters per second, we had a range of 14.28 meters. And with a horizontal speed of 15 meters per second, we went 21.42 meters. Do you see the connection between those numbers? 21.42, 14.28, and 7.14. If you said they're just multiples of each other, you're right. What this indicates is that, if you neglect air resistance, if I fire a cannonball with a horizontal speed of, say, 5 meters per second, then it's going to keep traveling at 5 meters per second, at least in the horizontal direction. And its downward speed will increase due to gravity, but its horizontal speed will be the same. So these are ideas maybe you explored in your grade 11 course, maybe not. If you haven't, I would definitely encourage you to keep playing around here. But they are the building blocks behind, modeling projectile motion. So let me go back to my note here. So Galileo was the first to devise that a projectile, is controlled by 2 independent motions. So an object presented horizontally will reach the ground at the same time as an object dropped vertically, which we've just illustrated. And no matter how large the horizontal velocity is, the downward pull of gravity is always the same. And we all know now this, observations, even from our grade 10 math course, right? If you think back to your quadratic relations unit, a ton of the examples you did were projectiles. That's because a projectile is going to follow a parabolic path. So I have a little visual for us in a second. But the definition of projectile motion is this. It's motion with constant horizontal velocity combined with a constant vertical acceleration due to gravity. So throw something in the air, it's going to follow a parabolic path with a constant horizontal velocity and constant vertical acceleration due to gravity. Now, that gravity could be different depending on where you are on the Earth or on the moon, where it's drastically different. But if I hit a golf ball on the moon, it might accelerate slower down towards the Earth, but it's still going to follow a parabolic path. I want to get a little visual of vectors. So this kind of simulates the cannonball. So what we had, if I can find my cursor. Where are you, cursor? There you are. If we launch some projectile with some horizontal speed, I'm going to call it Vx. If initially we launch it horizontally, then v1y, the initial speed in the vertical direction, would be 0. But after some amount of time goes by, the acceleration due to gravity has caused there to be some vertical component of speed as well. So at this particular point in time, the object has the same horizontal velocity, but now due to gravity, it has some, I think actually, yeah, that's fine. We're just going to leave it like that. It gets the point across. It now has some non-zero vertical component of speed. And at every stage of this diagram here, we have equal time increments going by, but we have the same horizontal velocity, and the vertical component of velocity keeps increasing. So I'll just do this a couple more times. V4y, and then I'll call this V5y. It finishes off here. Yeah, I like the way that looks. Vx and V5y. So two different motions, constant in the x direction, horizontal, and then constant acceleration due to gravity in the y direction. So what you do get is that initially you might have this horizontal projectile. Then after, where's my cursor again? After a certain amount of time, the velocity, if we take it, if I just say call this V2, the velocity will be somewhat down and to the right in the case of our diagram. And at every kind of instance, we have the velocity increasing. The length of that vector is getting longer. And the direction is changing too. As the object accelerates downwards, that velocity vector is being dragged down as well. So what we're going to be doing when we do our projectile motion examples for the next little bit, we have all the tools to do it. We know how to analyze constant motion in one direction. We know how to handle motion in one direction with a constant acceleration. And we know how to recombine vectors to get some resulting vector. So we know those things. So we should be able to analyze projectile motion. So let's actually talk about what equations govern projectile motion. So there's two governing, or there's two directions. So there's kind of two sets of equations that govern projectile motion. So the first is in the y direction. We have constant acceleration due to gravity. And the equations that govern our projectile motion are just our big five. Just you'll notice it's our big five with y subscripts to indicate that these are all displacements, accelerations, speeds, velocities in the y direction. Just like we've been doing when we did some review earlier, you'll often want to choose a direction in the vertical to be positive, and it doesn't matter which direction you choose. You just got to be consistent. So for maybe if I choose up to be positive, then my acceleration is going to be negative 9.8 meters per second squared. But if I choose, say, down to be positive, then my acceleration would be positive 9.8 meters per second squared. Along the same lines here, if I had, maybe consider some object being thrown off the cliff down into water. In this case, if I choose down to be positive, my displacement is in the downwards direction, and my delta dy would be positive. But if I chose up to be positive, then my displacement would be in the negative direction. So, it's just pick a direction that makes sense for you, that you feel comfortable with, and go with it. Mathematically, we all get the same answers. Our signs are just reversed. It's not too big a deal, but yeah, just pick a direction, be positive, and go with it. In the horizontal direction, we have one governing equation. It's horizontal speed is constant, and so speed equals distance over time. That's all there is to the horizontal direction. Now, if you wanted to throw in air resistance, things would become a lot more challenging. So we keep things simple. It's constant horizontal speed due to ignoring air resistance. So those are our governing equations. A couple other things. So if an object is projected horizontally, you will note that the vertical component of speed is 0. And the entire initial velocity is horizontal. So Vx, that's all this is saying right here, is that, get back to my black, is saying that all of the initial velocity, all the initial speed is in the x direction. V1y is 0. And I'm in the habit of referring, for a projectile, the initial speed to be the muzzle speed of the projectile. So when you hear me say muzzle speed or muzzle velocity, it's the speed with which the projectile leaves the cannon or like jumps off a cliff or what have you. In the case where the projectile is not launched horizontally, I'm just going to draw a little diagram down below here. So let's say our muzzle speed is v0, but our projectile is launched at some angle. Call it phi, like so. We now have experience together breaking things down into components. We can at any phase during a projectile's motion, we can break it down into a vertical component and a horizontal component. That's obviously the horizontal. Fix that up. So we have Vx, you'll have a horizontal part, and you'll have a vertical part. And using right angle triangle trigonometry, you can see that Vx, if that angle is with the horizontal phi, Vx is adjacent to that, then Vx is equal to the muzzle speed times the cosine of the angle. And V1y is the muzzle speed times the sine of the angle. And so you can get those. So just the same principle works if we had a projectile launched below. We have our Vx angle below the horizontal and V1y. And right angle triangle trigonometry, Vx equals V0 cos phi, and V1y is V0 sine phi. Those give you the speeds. And you just have to keep in mind which direction you chose as positive to say that whether that's positive or negative, your V1y. As we do more examples, hopefully you get more comfortable choosing a sign convention and working that stuff out. At any point, if we know the object's horizontal component of speed and vertical component, we can combine those to get the instantaneous speed and instantaneous velocity if we find the direction as well. And we can get that stuff just using grade 10 math. If we know the components at any time, we can find the instantaneous speed by using Pythagorean theorem. And we can find its direction using the tangent ratio. And if we put those two together, we get the instantaneous velocity, that speed combined with that angle. So we'll do that in the next example, I believe. So let's get to it. So we're going to do a horizontal example to start, and then our next lesson we'll do some examples where we're not launching our projectile horizontally. Back in the day when we were using cannons instead of satellites and drones and stuff like that, it was somebody's job to kind of figure out, hey, how should we how should we position our cannons, or how much gunpowder should we use in order to hit our targets, right? Because you don't want to be just doing this on the fly and wasting cannonballs while they're firing back at you. You want to be able to hit your target. So here we have a cannon on top of a tall cliff, and it aims its barrel horizontally at the ship in the distance. We know a few things. So we have that the water below is 56 meters. So I'm just going to add a few things to my diagram. So I'm not saying that's positive or negative yet. I haven't chosen a sign direction. This is just a physical diagram of the problem. And the ship is 250 meters away from the cliff. And we'll just assume like that means like the center of the ship. And we're firing a cannonball with some horizontal speed, and we are firing horizontally in this one at 60 meters per second. So what we know is that the cannonball will follow a projectile, or the motion of a projectile, and is going to strike the water. So what we want to find out is, hey, if we launch this cannonball at 60 meters per second, are we going to hit the ship? And what we'll do together is we'll find that out. And if we find out it hits before the ship, we'll find out how much distance is remaining. If it flies past, we'll find out that too. Afterwards, well, spoiler alert, it's not going to hit the ship. In part B, we'll solve for something different. We'll work backwards and find what velocity do we need to strike the ship. And then C, we'll get some practice finding a velocity combining our two directions of motion. So let's get going with part A. So with part A, we are finding if the cannonball will hit the ship. So first, let's choose a sign convention before we do anything. So you can do whatever you like. I think to mix this one up, I think in the last example I did involving a projectile that we just dropped straight down, I think I chose up as positive. I'm just going to use down as positive in this time. Maybe for questions where your projectile is going from some height to down below, maybe that connects with you, using that direction, downward direction, to be positive. But ultimately, it doesn't matter. And so what do we know? So if we choose down to be positive, our acceleration will be positive 9.8 meters per second squared. From the description of the problem, our displacement in the positive direction, 56 meters. So in this case, we do need to specify that is our displacement in the y direction. So delta dy, 56 meters. What we are interested in finding, and maybe I should say one more thing, since this problem is a horizontal projectile, v1y is 0 meters per second, and our vx in the horizontal direction is 60 meters per second. What we're interested in finding is how far does it travel? So in general, the key idea for most projectile motion problems is that time is kind of the connecting factor between both directions. We can find, using our kinematics skills, since we know an acceleration, the displacement, and the initial speed in the vertical direction, we can find the time it takes for the cannonball to hit the water. It's the same, the time it takes the cannonball launched horizontally to hit the water, it's the same as if we had just dropped it. So we're going to find the time it takes a cannonball to drop and hit the water. And then we're going to find how far horizontally that cannonball travels in that same amount of time, traveling at a constant speed of 60 meters per second. So that kind of outlines our strategy. So let's get started doing that. So the first thing we'll do, and this is how I'm structuring my solution. You don't have to do that by any means, but in this problem, we want to find delta t. We want to find when we're striking the ground. So even though the question didn't exactly say find the time, we do need it. And if we look at what we have in the vertical direction, we have acceleration, delta dy, and v1y. And so it makes a lot of sense for us in this particular problem to use this equation of motion. Delta dy equals v1y delta t plus 1/2 a delta t squared. This is our displacement curve equation from Big Five, just with subscripts of y. And this one's actually really practical too, because v1y is 0. It actually makes the equation easier to work with. And so we know delta dy in A. It's easy for us to solve for delta t. I'm actually just going to rearrange for delta t in this one. If I multiply up the half, I get 2 delta dy equals a delta t squared. So to get delta t by itself, I'm going to divide by a and then square root. So delta t equals 2 times delta dy divided by a, and we'll square root. And we have those things, so let's plug them in. So 2 times 56 meters divided by 9.8 meters per second. Just want to double check, it is 56. Yep. So as we're doing that calculation, think about what would happen if we let the upwards direction be positive. We'd have a being negative 9.8, but we would have delta dy being negative 56, and that those two negatives would divide out, and we would get the exact same answer. We get a positive result inside the square root, and when we square root, I get about 3.4 seconds. This is the time it takes to hit the water. Now we can ask, well, how far did we travel in those 3.4 seconds? Well, remember our equation of motion in the x direction, there's just one. It's for constant speed. Vx equals delta dx over delta t. And we can find delta dx by rearranging that, by doing Vx times delta t. So a cannonball traveling at 60 meters per second for 3.4 seconds, well, how far does it travel? Let's find out. 60 times 3.4. So it travels 204 meters. And so we now know, since the ship is 250 meters away, that we are short by 46 meters. So obviously a speed of 60 meters per second is not enough. Maybe we need to pump more gunpowder in to give it a higher initial speed. So that begs the question, what speed do we need in order for our cannonball to travel 250 meters? We've done our first example, an example of finding kind of like a horizontal range. So let's go on to part B. In part B, we're going to find what velocity is required to strike the ship directly at water level. So I'm going to actually just kind of write out what we know. Now, what's changing with this problem is that now we want to strike directly here. Our acceleration is still 9.8 meters per second squared. I should note, I'm still going to use down as positive. Our delta dy is still, green was a horrible choice for the background here. I'm losing my cursor. Delta dy is still 56 meters. v1y equals 0 meters per second. Just writing out the things we know. Now, actually, we know the time it takes to reach the ground, right? It doesn't matter how fast you project this cannonball horizontally. We found out that it's going to hit the water in about 3.4 seconds. So that might be useful. What we don't know is, we do know that delta dx, we do know the range in this case. It is 250. That's our desired horizontal distance. What we want to find out is, what horizontal speed do we need? So by writing that stuff out, we can kind of make some connections. So guys, if we're given the two of the three things in that horizontal speed equation, we can find the third. If you know how far it needs to travel horizontally, and you need to know when it hits the ground, you can find what speed you need to cover that distance in that amount of time. So let's do that first. So we're going to find Vx. And Vx equals delta dx divided by delta t. Here it's 250 meters in 3.4 seconds. So we're expecting something, a little bit bigger than 60. 250 divided by 3.4. I'd say call that 73.5 meters per second is the horizontal speed we need to get to that ship. And actually, I believe that's just the what initial velocity is required. Yeah, since we actually, that's it. It's the speed required. We don't need 2 steps. It's because we found this delta t. Now, if we say we hadn't done part A, we would need to find that time it takes to hit the water. So time is always that connecting factor. But in this case, we had the time, so we just used it. But yeah, 73.5 meters per second would get us there. And the third stage of our problem is, okay, what is the impact velocity going to be? So now that we know that that horizontal speed of 73.5 is going to get us to hit the ship. At this point, the velocity will be kind of impact velocity. It's going to be kind of down like that. There'll be some horizontal component, some vertical component. And that's what we're trying to find in part C. So remember, velocity, that impact velocity implies we need the speed and direction at that point. We know the horizontal component of speed is 73.5 meters per second. But how fast vertically is the cannonball moving at that point when it strikes the water? So let's go into one more frame here. And I mean, you don't need to rewrite all this stuff if you would prefer not to. Some of you may prefer to, depending on your comfort level. But at least for now, I'm just going to rewrite the things I know. So again, I'm just going to leave up as positive. And we have traveled 250 meters. Our delta dy is 56 meters. Our v1y is 0 meters per second. Our vx we have found to hit the ship, 73.5 meters per second. The one thing we need to get the impact velocity is we need to know what the final vertical component of speed is. We don't need a final component of horizontal speed. It's always the same. It's 73.5 meters per second. So this is what we need. And we're going to be using, we know the time to reach the water, 3.4 seconds. So let's find V2y. And we have a handy dandy equation of motion that helps us do that. V2 equals V1 plus A delta T. In this case, we're using R subscripts Y. V1y is 0. And so we just have, we're accelerating for 9.8 seconds from rest for 9.8 meters per second squared for 3.4 seconds. We know that the units are going to pop out meters per second, 9.8 times 3.4. So I'm going to say to call that 33.3. And now we're going to put it together. So we know at impact, we have a horizontal component of speed of 73.5 meters per second. And we've just found out at impact, the vertical component of speed when we strike the water is 33.3 meters per second. And here's where our work with vectors comes in. We can now find this impact velocity just by using Pythagorean theorem and the tangent ratio. So the size of that impact velocity is just the root of 73.5 squared. This is just Pythagorean theorem plus 33.3 squared. And then to get the angle, we understand that it's going to be below the horizontal. The cannonball is traveling downwards. Be the inverse tan of 33.3, the y, over 73.5, the x. And let's just finish this off. And we got it, guys. So 73.5 squared plus 33.3 squared and square root. So the cannonball strikes the ship at about 80.7 meters per second. And the angle, we do 33.3 divided by 73.5 second tan at an angle of about 24.3 degrees below the horizontal. So we can wrap this up. Impact velocity V is 80.7 meters per second. And for the direction, we can say 24.3 degrees below horizontal. I'll just put a little dot there for short form. All right, so we've kind of solved 3 different types of horizontal projectile motion problems. Other problems, may ask you to find a delta dy, may ask you to find. I think we found delta dx. We found a vx. Yeah, we've covered a lot of the bases here. So you should have a good starting point for solving a few horizontal projectile motion problems. A good starting point is just using the graphs method, guys. Write down what you're given and what you're required. If you go back to your governing equations, it's often going to give you a clue of what to do. If you've got 2 of the 3 things here, then you can find the third, right? And then time is the connecting factor between the 2. If you know any of the 3 of the 4 things in these equations, then you can find the 4th, right? But just takes practice. So I've provided you guys some practice. Hope you guys give that a try. After you've done a bit of practice, we're going to do some problems where we launch a projectile above the horizontal or even below. And we do the same process here. It's just in the problems we do moving forward, V1y is not going to be 0. So that makes the math a tiny bit more complicated, but we're going to pretty much use the same tools. All right, that's it from me, guys. I'll see you next lesson. Hope you stay well. We'll see you soon.